last class I had asked you a question related to the RLC series circuit, where the circuit was like this and you were asked to predict the waveforms. And I could see that in this case you are somewhat confused. So, let us revisit this issue. In this case, your applied voltage waveform was like a step. So, it was step input like this up to some voltage V. So, the question was what would be the waveform for the VR, VL and VC. So, how would you argue with it? How argue about it? We had decided that the current waveform that we did yesterday, the current waveform should be I over T. How was it? Turn the page. Turn the page. It should rise and then it should decay like this, right? And when it rises, there was a slope here. That is also what we decided. What was the slope? So, this slope is V by L, fine. So, if this is so, then your VR should be exactly proportional to this, because VR is R times I, no problem about it. But the question is what would be the waveform for VL and VC. That is where I had asked you to work it out at home, draw and show me. So, let us see what you have done. Teja is smiling, but nevertheless let me try to figure out how it will look. Bolo. So, what is your logical conclusion about it? So, we are trying to work out VC against T and VL against T. Notice, when you try to work it out, first talk about the extreme condition. What will be the value when T is equal to 0 and what will be the value when T is equal to infinity? First work this out. So, what is the value when for VC? What is the value for T is equal to 0? Obviously 0, because it is not starting with anything. So, it starts from here. Where does it end? V. Good. So, you will have the value V here and then it should reach like this. But you can easily see there are two possibilities of doing like this. One is like that. Will it go like this? Will it go like this? Let's consider exponential rise up to this value. Is it correct? So, here the moot question is dVc dt, that means the slope here. So, what is dVc dt? Yes. So, I will write here dVc dt is equal to I by C. I at the initial condition is 0 and therefore, I by C is 0. So, dVc dt must start at 0. So, it cannot be like this, it must be like right. Now, come to VL, what should be the waveform like? It should be going down and up. Okay. How would you decide about this one? Ultimately, you have to talk about when it starts, what is the value of VL. No, what is the value of VL? VL is L di dt. So, always VL is equal to L di dt. So, VL's value will be the starting value of, obviously. Now, you see initially current is 0, therefore, the voltage across this is 0, voltage across this is 0, therefore, the whole voltage appears here. So, starting point has to be V. Okay. So, it starts from here. After that, after an infinite amount of time, what happens? The current again goes to 0. If current goes to 0, then di dt also goes to 0, and therefore L di dt goes to 0, it has to be 0. So, starts from here, ends here. It could be like this, it could be like that, it has many possibilities. So, what is the real thing? The point is that it has to always follow the derivative of the current function. Current function's derivative initially starts with v by L, and times I it will be is v. So, it starts with the slope starts with V L, starts with what value? V. But then what will be the okay? So, it ends at infinity. At this point, what will be the slope? Which requires dVL dt. Okay. So, we will be then interested in dVL dt. What is it? That will be obtainable from the equation itself. Look at the equation. Yesterday we did it. Look at the equation. What was the equation last time? We had written the equation as V is equal to R I plus it will be L di dt plus 1 by C integral I dt, right? And we had integrated it or differentiated it to get 0 is equal to R di dt plus L d2, here it is, plus I by C. So, if you are talking about this term, we are essentially talking about this term. It will be minus R di dt minus I by C. I initially is 0, but di dt is not 0. So, it will have a slope, negative slope. It will drop at a negative slope like this. Fine, but will it go like this? No, because the slope reduces and finally goes to 0 and then goes negative, and so it has to go negative and then it has to go like this. Fine. So, does it logically sound? Just quickly let us check it on the computer. We had, I will just go to the bond pad. Now, here we can see that I had simulated earlier the LCR circuit with a source of effort. We had already given the numbers, we had already given the power directions, and if I view without the circles, we had also have the causalities. So, the next step would be to generate equations. So, we can generate equations here. The next step would be to generate the simulation code, which we had saved. Yeah, good. And then we have to compile it. Fine. Now, we have to enter the parameters and then we have to simulate. Good. So, let us say AC1, just 1. I need to put in values for which it will be exponential, that means should not go into the oscillation mode. So, what will be the R? I will put a somewhat large value of R. M2 would be say 1 and this would be somewhat large value. Check that, check if for these values, that means AC not necessary, R 10, M or that is the value of L is 1 and K3 which is the capacitance is 10. Just check if it is giving the correct result or is it giving, anyway we can check here also. So, we will give the time duration say maybe 2 seconds and then we simulate. We have not given the plot blocks. So, 0, the horizontal is time, vertical 1 I will give P2, and vertical 2 I will give Q3. Okay. So, that is what you expected. Notice that Q3 is the voltage across the capacitor, it starts with 0 slope, that is what we predicted. It goes up and tries to reach the final value V. The current goes up and down like this, that is what we predicted. So, what we predicted logically were actually correct. Now, the question is, I had asked you this question and I was surprised that nobody objected. What would be the time constant in such a system? See, I had in passing said that if you have a two-dimensional system and if the parameters are such that you have exponential response, then you can work the same way to obtain the. But now, notice this and let you try to argue out what will be the time constant or the concept of time constant in this case. Notice here it is rising like this, here it is rising like this. This is actually a combination of yes, not only two time constants, the exponential functions, a combination of exponential functions. And we had earlier seen that the expression of this is, the expression will be something like e to the power minus zeta omega n t C1 e to the power omega n root over zeta square minus 1 t plus C2 e to the power omega n minus omega n root over zeta square minus 1 t. You notice that this is a exponentially rising function and this is exponentially decaying function, and the whole thing is a combination of these two. So, that is why it rises and then falls. For some time this dominates, for some time that dominates, and then the whole thing is multiplied by this term, which is a exponential decaying term. This essentially ensures that for very large values of t, this would be going to 0. But now there are 3 different time constants here. So, that will have to be taken into account in this case. So, there is no unique time constant in this case. Look at this waveform of the voltage. It was ultimately reaching this value V, but it was going like this. What was the logic in working out the time constant? We said that if the starting slope continued for some time, at what time will it reach V? So, at what time will it reach V? It will not never reach, because it is 0. Okay. The other point was that yes, you can argue that, you can say at what time does it reach 0.63 of that, but essentially that came from this logic, that if it continues it will reach. So, in this case it would be somewhat meaningless to define the time constant. By the way, how will the waveforms look if the parameters are so chosen that you have sinusoidal response? First, the current. If you have an exponential response, it is like this. If you have sinusoidal response, how will it look? Yes, there would be a sinusoid with a decaying amplitude. So, there will be a sinusoid with a decaying amplitude like this. In this case also, you cannot define the time constant in the same way, but there is an exponential term. So, instead of time constant, we can say that there are certain characteristic times in the system. One characteristic time relates to the time constant as obtained from the exponential. Another characteristic time relates to the time constant or the characteristic time of the sinusoid, period of the sinusoid. Okay. So, in this system, therefore, there are 2 characteristic times. So, instead of time constants, we will try to think in terms of characteristic times. And in more complicated systems where you have higher dimension, 4 dimensions, 5 dimensions, it is not difficult to see that there would be many such characteristic times. There will be some exponential terms, there will be some sinusoidal terms. If there is a 5 dimensional system, there could be one pair of complex conjugate eigenvalue, another pair of complex conjugate eigenvalues, they individually giving rise to different characteristic times of the sinusoid, omega different. So, a system can have many characteristic times within itself. And if you are having to solve it by numerical means, then different characteristic time means, one says, suppose one is very short time, that means a fast time constant, the other is a slow one, that means characteristic time is rather large. What does it mean? It means that it has two sinusoids in it, one has a very long time duration, the other has a very short time duration. A situation that would happen, for example, when you have the motor with the shaft between the motor and the load, and we said that in order to make it differentially causal, integrally causal, you have to assume some kind of a stiffness of the shaft, but that stiffness of the shaft will be, it will be very stiff. So, if it at all vibrates, it will be vibrating very fast, much faster than the characteristic time of the other rotations. Okay. The result will be that the problem will be very difficult to solve numerically. Why? Because all the time in the numerical routines you are trying to set the h, the step length, depending on the difference between what you are calculating by, say, third order Runge-Kutta method and fourth order Runge-Kutta method, and all the time it will try to reduce it, because all the time it will see differences if you have such very sharp oscillations in it. Such systems are called stiff systems, where it is difficult to solve it. So, in a system, if there are different characteristic times which are very different, then it becomes rather difficult to solve. Technically it becomes rather difficult to solve, and in reality also such systems are relatively difficult to handle, because there would be ringing, there will be vibrations at higher frequencies. So, we normally try to avoid such systems. Okay. Now, let us go ahead with where we were last time. We said when we broke off the last day, we were what were we doing? We were doing a sinusoidal excitation on a RC circuit. So, you had a RC circuit with a sinusoidal excitation. RC circuit with a sinusoidal excitation, and we had decided that it would be given by a equation of the form IP would be given by an equation of this form A cos omega t plus B sin omega t, and then on that basis, on the basis of the logic, that the solution actually tries to follow the change or shifting fixed point. So, wherever the fixed point goes, accordingly the solution also tries to follow. Based on that logic, we had guessed that this solution will also be a sinusoid. Notice that somewhat like this logic you have also come across in mathematics classes, because how do you actually solve? You try to fit into some trial solution. Remember that? Now, often when you learn that, how does this trial solution obtained? How is this trial solution obtained? Or in a general case, general situation, how would you guess a trial solution? That is often not very clear to students. That is why I went by that logic. The reason, the whole logic rests on the fact that the solution also tries to follow the fixed point, and therefore it should have the same functional form as the fixed point, as the motion of the fixed point. And that is why we had guessed it, and we had arrived at the expression from there. A is equal to, just recall, omega c V m divided by 1 plus omega square c square r square, right, and your B was omega square r c square V m divided by 1 plus omega square r square c square. Fine. So, this we had obtained in the last class. So, we will plug it in and obtain the total solution. So, your solution would be I p is equal to omega c V m by 1 plus omega square r square c square cos omega t plus omega square r c square V m divided by 1 plus omega square r square c square. Now, let us try to express it, let us try to take some common and let us try to express it in terms of something cos omega t plus something sin omega t, so that we can express it as sin omega t plus theta. Okay. How would you go by that logic? How would you do the algebra? How would you do the algebra? Yes, but if you keep just like that, it does not come in that form. So, we need to get something out. So, the point is that it has to be something cos omega t and something sin omega t, right, and those some things should be expressible in the form of cos theta cos omega t sin theta sin omega t, then it gets in that form. Okay. So, try to express in that form. Okay, what do you take out? Omega c V m by root over and then what remains? Wait, suppose something cos omega t. Now, if you take the whole thing common, it remains just cos omega t. Yeah.
So, inside we will have another root over 1 plus omega square r square c square.
How does it help?
So, cos omega t by root over 1 plus omega square r square c square plus omega r c
wait,
sin omega t by
wait. It will be far more easier if we keep this. I'll write it separately. If you keep 1 by omega c cos omega t plus r sin omega t, you will see how what I am driving at. So, in order to do that, because r was here, r was not here, this is omega square c square, here is omega c. So, we can appropriately take common. What comes common? It is V m divided by 1 plus omega square c square divided by that. So, you have so divided by omega square c square, it becomes r square plus 1 by omega square c square. Check. So, this is here is 1 plus omega square c square, omega square c square goes above. So, that is what we have taken common. So, this remains. Okay. The advantage is that whatever appears here also appears here. That is what we wanted. Then we say that okay, now z sin phi is 1 by omega c, z cos phi is r, okay, which means z square is equal to r square plus 1 by omega square c square. Fine. This means z square equal to r square plus omega square c square. You can easily see what I am driving at. This means that if you have r here, omega c here, this is Z, R 1 by omega c, this is Z, and then this is, this means exactly that. Fine. By doing this manipulation, what we have actually obtained is, in that case your tan phi is 1 by r omega c. Fine. Okay. In terms of this equation becomes, then this equation becomes I p is equal to V m, it was by this, so it is this is Z square, is it? This is Z square in the denominator. So, and this is equal to sin phi cos omega t plus cos phi sin omega t. Fine. This is equal to V m by Z into sin omega t plus. So, simple thing, we started with a big thing, but actually it is a simple thing, and that is what we actually know. That is what we did in the first year actually, when we started with the LCR circuits and sinusoidal voltage. But then why did we write P? Because it is a particular, this is the steady state solution. We had learned only the steady state solution, and this is exactly what we obtained. Fine. So far it matches with what we intuitively understand, but there will be also a transient part, and the transient part in this case will be a something that is damped, something that is exponential. So, we can guess that the complementary part will be some k times e to the power minus t by R c. Where do you get the k from? K has to be obtained from the initial condition. But now notice that the initial condition has to be initial condition of the total current, which is the addition of these two, not just obtained from here. So, your total current is I is equal to I p plus I c, your particular integral and the complementary function. They taken together, you have V m by Z sin omega t plus phi plus k e to the power minus t by R c. Fine. Now, we have to obtain this from the initial condition. Suppose the initial condition is where the charge stored in the capacitor is 0. That is a reasonable initial condition. Charge stored in the capacitor is 0. So, what will be the initial current? Applied voltage, whatever is the applied voltage, you have to notice I am telling something that is important. Applied voltage is a sinusoid. So, what is the initial condition that applied voltage? Depends on the phase. You cannot say that something is the applied voltage. The applied voltage could be 0 if it passes through 0 at the instant of switching on. If the applied voltage initially is 0, then your current through is also 0. If it is not 0, then current through is not 0. Fine. So, you see, supposing let us start with the condition that the initial current is 0, the applied voltage has been switched on at the moment of 0 crossing. in that case your the current is 0. So, this should be at t is equal to 0 yield 0 in the in this side. So, what is the this side at t is equal to 0? What? V m by z sin phi plus k. Fine. So, you know what sin phi is, we are already written down, substitute that here. Or we can do it somewhat easily. The particular integral term was this, at t is equal to 0 this should be 0, the whole thing would be 0, this would be 1, and therefore, this should be the remaining term. So, you can say this term should be omega c v m divided by 1 plus omega square c square r square. Fine. So, you have the k minus this, and therefore, the actual current, the total current will be I is equal to I p plus I c, which is V m divided by your z, which is r square plus 1 by omega square c square sin omega t plus phi, which is tan inverse 1 by omega r c. This is the I p part plus, oh sorry, it will become minus, because k is minus of this, minus omega c v m by 1 plus omega square c square r square. Yes, that is enough. Then e to the power is visible, e to the power minus t by r c. So, that is the total solution. Fine. So, this is how you obtain the total solution for a case where a sinusoidal voltage is applied at some instant. But this will not be the total solution if you switch it on at a different time. If you switch it on at a different time, there would be this will yield something else at the initial instant, fine, and you will have to obtain the k from that. So, in general there would be one term which is the exponentially decaying term, which will represent the transient, and this will be the steady state term, this will be the steady state term, and this will be the transient term. Okay. Fine. Now, there is a condition under which there will be no transient. Can you find it out? There will be a condition under which there will be no transient. Your differential equation was L, oh sorry, it was okay, we'll come back to that. Just think about this particular problem, that here we have different results of this if you start the sinusoid at different points, different phases. We'll come back to this particular issue. When k is 0, you are right. Yes. So under what condition is V m by z sin phi 0? So that would be a question then. So it is important because there are certain conditions under which you would like to avoid the transient. So it is necessary in a dynamical sense to understand under what condition will there be no transient at all. Okay, we'll come back to that. but first let us try to see what will happen in case of R L circuit. Apply a sinusoid across a R L circuit. In that case, simple, you have the equation as L d I dt plus R I is equal to V m sin omega t. No problem here. So, we proceed exactly along similar line as we did the last time, and then we can conclude. What we can conclude? We will conclude exactly the way that we even learnt in the elementary electrical engineering classes, that the solution will be the steady state solution, the particular one will be this sinusoid and this seen as a z, which is omega L and R. So, we will construct a triangle like this. This is omega L, this is R, this is Z, and the solution would be I P would be V m by Z sin omega t minus phi. Okay. So, let us skip all these algebra that we did, because it follows exactly the same route. It is not necessary to repeat all that again. We will arrive at this. And what about the, in this case, what is Z? And phi is so there is no difficulty. The complementary function will be I c, again will be a similar thing, k e to the power minus, what is the time constant now? No, in something times t r by L. What?
Here it will be L by R. Percent is R by L. So T by tau.
Oh, yeah. Okay, let us write it like this. This is correct, but this time constant is L by R. Yes. So, I c is k e to the power minus, I am not writing as t by tau, I am simply writing as r by L t, yeah, which is k e to the power minus t by tau, tau is equal to, right. Is this right or wrong? Okay. So, the complementary function will be of this form. Again, we will have to find it the same way depending on the initial condition. So, now suppose the sinusoid starts with some phase. If the sinusoid starts with some phase, it will be L d I dt plus R I is equal to, then we will have to write V m sin omega t plus some theta. Okay. So, this will be the original equation whose solution we are trying to obtain, and the solution will be your I is equal to I p plus I c is equal to I p is V m by Z sin. Now, in place of omega t, we had the original one like this. In place of omega t, we will have to write omega t plus theta minus phi, okay, plus this term k e to the power this one minus r by L t. Now, at the initial condition, this is 0, this is 1. So, you have at the initial condition the current is 0 because it is inductive circuit, you cannot have the current changing instantaneously. So, 0 is equal to V m by Z sin theta minus phi plus k, okay. Or k is equal to minus this. So, k is equal to minus V m by Z sin theta minus phi. Now, you notice that if theta is equal to phi, then this term is 0, therefore, k is equal to 0. If the k is equal to 0, then the transient is 0. So, what is the condition that the transient will be 0? That if the system has a phase angle phi, then if you start the sinusoid exactly at that amount of delay, then the transient will be 0, clear. And this the decision will, the conclusion will be the same for the RC circuit which I asked. We have done it for the RL circuit, but the RC circuit the conclusion will be the same, fine. So, here we have more or less done the situation for first order systems excited by the sinusoidal excitation. Is there any question on this kind of systems? More or less I have done it exhaustively. Okay. Now, comes the question, if you have a second order system and excited by a sinusoidal excitation, what will be the situation? Second order system means an RLC circuit or a mechanical system, something like this. All the time you have to keep in mind that we are talking about a situation also like this. A mass, spring and damper, and there is a forcing function which is your F sin omega t. So, you have got a mechanical system whose applied force is a sinusoidal force F sin omega t, and there is a mass, spring and damper. That is a equivalent of a circuit something like this. So, their dynamics will actually be the same. So, in that case, how would you proceed? First, write down the equation of this circuit. Let us proceed with the circuit example, and then we know that it is equivalent to the mechanical example. So, you have V m sin omega t is equal to R I plus L d I dt plus 1 by C integral I dt, fine. We differentiate it through, we have R d I dt, I am writing the right hand side this side, plus L d 2 I dt 2 plus I by C is equal to V m omega cos omega t, right. What would the solution be? This is the equation, a second order differential equation. What would the solution be? Again, go by the same logic. It is a sinusoidal excitation, and therefore, the equilibrium point is also moving sinusoidally, and therefore, the actual state will try to follow it, and therefore, it is logical that it will also be some kind of general sinusoid. Again, we will write the solution, a trial solution. as here we are talking about the steady state solution. So, I p is A cos omega t plus B sin omega t. How would you obtain these values A and B? Simply by putting it here. So, we will first obtain from IP will be substituted here. You have to first obtain dip dt, which will be substituted here, d2i dt2 will be substituted here. So, write down these two and substitute it here, and thereby you will obtain the result. So, your dip dt is minus A omega sin omega t plus B omega cos omega t, and yeah, d2 ip dt is equal to A omega square cos omega t plus it is minus B omega square sin omega t. So, we have the first thing is different derivative is double derivative. So, just substitute it here. Okay. Plug it in here. You have first r times this, so it will be first we will take this one L times this, it is L A omega square cos omega t minus B L omega square sin omega t minus, now the first derivative term, A r omega sin omega t plus B r omega cos omega t plus the original term A by C cos omega t plus B by C sin omega t is equal to the forcing function V m omega cos omega t. What was the next step? This will hold true if the coefficients of the cosine terms are 0 and the coefficient of the sine terms are also 0. This will give this term. First, let us put together the cosine terms, minus L A omega square plus V r omega plus A by C cos omega t plus minus B L omega square minus A r omega plus B by C sin omega t is equal to V m omega cos omega t. This immediately yields this is equal to this and this equal to 0. Fine. So, write this and then obtain A and B from there. Two equations, two unknowns, you can do it. Minus L A omega square plus B r omega plus A by C is equal to V m omega. That is one equation. The other is minus B L omega square minus A r omega plus B by C is equal to 0. From here you will obtain. See, though the algebra looks a bit involved, ultimately the things are conceptually rather simple. So, you have to obtain A and B from there. just do a bit of practice, because if I ask you in the exams, otherwise you will get messed up. So, from here you will have to obtain A and B. A comes out to B. I will skip all this algebra, which you can easily do yourself, but I will just write the result V m. Now, I will also arrange it in a bit more intuitively understandable form. I will write 1 by omega c here minus omega L here, and this is 1 by omega c minus omega L whole square plus r square. B is comes out to be V m r. Here it is 1 by omega c minus omega L square plus r square. So, immediately things fall in place, because then this will be the component that you draw like this. Here it is r, here it is 1 by omega c minus omega L, here it is z, which means your z sin phi is 1 by omega c minus omega L, and z cos phi is equal to r, and you have z square is equal to r square plus 1 by omega c plus omega L square. Okay? Huh? Fine. So, everything now falls in place. Your final solution is I p is equal to I p is equal to well, it will be again V m by z. Then we will write it is sin omega t cos phi plus cos omega t sin phi is equal to V m by z. You have sin omega t plus phi. Phi is now obtainable from here. So, this is the particular integral. What about the complementary function? See, obtaining the steady state solution is not difficult, because you already know that if you have a RLC circuit, the way we do in electrical engineering is that R and then j omega L 1 by j omega c, add them, obtain it, you get the same thing. So, here so far I was writing a bit faster, because this is something that is already known. What about the complementary function? That might give you trouble. Yes. So, that might give you trouble. So, what will be the complementary function in this case? Yes. Wait a minute. It will be where you have not applied the sinusoid, you are considering the left hand side of the equation. Where was the equation? You are considering the left hand side of the equation, which is a second order equation. And if, I mean, there are two possibilities. If you obtain the eigenvalues, it could be real, it could be complex. Supposing they are real, then also two eigenvalues. Suppose they are lambda 1 and lambda 2 along the directions v 1 and v 2. Okay. So, if these were not there, then the solution would be the I will write it as not as I c, but rather the full vector x c t as we know e to the power c 1 e to the power lambda 1 t times V 1 is a eigenvector plus C 2 e to the power lambda 2 t times V 2, that eigenvector. Okay. In case of the first order system, this writing of the complementary function was rather trivial, but in case of the second order system, it would be that unforced system, its response will give you how the thing will decay, and it will be exactly like that. Okay. And then okay, if it is complex conjugate, then what will be the complementary function? If it is complex conjugate, what will be the complementary function? No. Yes, there will be sinusoids. Yes, we have already learned that, and that will be the complementary function. So, if for complex eigenvalues x c will be C 1 e to the power sigma t times, remember, we had obtained it, and this will be the complementary function. Okay. So, for real eigenvalues, this will be the complementary function. For complex eigenvalues, this will be the complementary function, and ultimately the total will be where is it? Yes, this plus either this or that. And then from the initial condition you will have to obtain the C1 and C2. Clear? Will not be clear unless you do problems, which I will give, and you will have to do in the tutorial class. But this will not be clear unless you actually do some problems like this. But conceptually should be clear that the unforced systems solution, its eigenvalues and eigenvectors should give the transient response, and the steady state response will be given by that. Okay. Now, notice that here there is a problem. There is a problem because this omega was that was the forcing functions omega. Yes, you have to keep in mind that. And this omega is natural frequency. So, it will be, say, let me separate them out, otherwise you will have confusion, you will mess them up. Notice that here there are two characteristic times of the system. One its own, if you let it oscillate by itself, its own omega 1, and the one that is there is applied on it. So, the actual dynamics will be a combination of these two frequencies. Clear? Two different characteristic times of the system, and I hope you understand how to proceed. We'll see and we'll do problems later. Okay, that's all for today.